When a hospital installs a titanium hip implant, the hardware remains physically identical from the day it is manufactured to the day it is removed. But when a hospital deploys a machine learning algorithm, the software actively adapts and shifts its internal weights as it processing new patient data. This creates an immediate regulatory friction point. Our entire framework for medical device safety was built for physical products that remain static after approval, making it extremely difficult to govern algorithms engineered to learn from real-world use. As an algorithm operates over months or years, it inevitably encounters covariate shift. Covariate shift is a statistical phenomenon where the underlying distribution of incoming patient demographics or clinical practices gradually changes over time, causing a previously accurate model to slowly degrade in performance. The standard mechanisms we rely on for patient safety cannot detect this type of degradation. For example, the FDA relies heavily on the MAUDE database to track medical device failures in the field. The MAUDE database is the FDA's central repository for receiving discrete, case-based reports of adverse events involving medical devices. Because systems like MAUDE are designed to catch discrete, catastrophic failure events, like a mechanical pump short-circuiting, they are completely blind to aggregate statistical drift. A model's sensitivity slowly dropping by 3% over a year does not trigger an adverse event report. This dynamic introduces silent degradation into the clinical environment. The model continues to output predictions with high confidence, and doctors continue to rely on those predictions, entirely unaware that the mathematical foundation beneath the system has decayed. Deploying continuously learning algorithms without a persistent mechanism to monitor and interdict aggregate drift means we are accepting invisible patient risk in exchange for technological advancement. Regulatory bodies recognize this vulnerability. To address it, the FDA introduced the Predetermined Change Control Plan, or PCCP, which allows manufacturers to pre-specify acceptable bounds for model updates without requiring a new regulatory submission. Across the Atlantic, the EU AI Act includes Article 43.4, a parallel provision that permits predetermined changes to an AI system without triggering a new conformity assessment. These policies authorize predetermined changes legally, but they provide zero engineering instructions on how a hospital or developer should securely execute them. They mandate that drift must be monitored and safety maintained without defining the operational logic required to do so. The AI/ML Evaluation and Governance Infrastructure for Safety, or AEGIS, bridges this gap. AEGIS is an operational framework that translates these abstract regulatory mandates into executable math. Policy alone cannot protect patients. AEGIS provides the exact mechanical layer required to make the FDA and EU frameworks functional, converting legal expectations into a deterministic, automated safety pipeline. To understand how the abstract AEGIS architecture operates in practice, we can look at its application to the PhysioNet sepsis prediction model, an algorithm designed to detect early signs of sepsis in ICU patients. To make an accurate prediction, this model ingests massive amounts of raw clinical data, processing 202 distinct features ranging from real-time vital signs to laboratory blood work. This architectural diagram shows the first invariant module of AEGIS, the Dataset Assimilation and Retraining module, or DARM. The DARM acts as the absolute gatekeeper of data integrity, enforcing strict separation of incoming clinical observations into distinct evaluation blocks. A portion of the data is locked into the golden dataset. This static, iteration-independent vault is never used for training. It exists solely to provide an unbiased benchmark, guaranteeing the model can be tested for regulatory substantial equivalence against a clean, unchanging standard. The remaining new data flows into the drifting dataset. This dynamic pool serves two purposes. It tests the live model against the hospital environment to monitor for decay, and once validated, it safely feeds back into the training dataset to teach the model. This compartmentalization is mathematically strict. Without auditable separation between the data used to teach the model and the data used to judge it, any subsequent safety guarantee is invalid. Once the DARM routes the data securely, it passes to the Model Monitoring Module, or MMM. This is the continuous surveillance engine of the AEGIS infrastructure. The MMM continuously calculates standard clinical performance metrics on the isolated data streams. It specifically tracks critical indicators like sensitivity and specificity, comparing the model's current performance against predefined clinical thresholds. Beyond basic accuracy, the module detects statistical drift by applying a Bonferroni-corrected Kolmogorov-Smirnov test to the incoming patient data. A Kolmogorov-Smirnov test is a statistical method used to determine if two datasets differ significantly, and applying a Bonferroni correction ensures we don't trigger false alarms when testing multiple features simultaneously. This allows the system to definitively flag when the underlying demographics fundamentally change. To synthesize these disparate signals, the MMM generates an MLCPS. The MLCPS, or Cumulative Performance Score, is a composite metric that projects multiple individual performance indicators onto a single unified score, based on domain-specific weighting. But the MMM has a strict architectural boundary. It is purely an observation engine. It calculates the metrics, logs the distributional shifts, and measures the decay, but it possesses zero authority to make a deployment decision. Passive monitoring without automated interdiction simply documents a failure as it happens. To improve clinical safety, the observations must be paired with deterministic decision logic. This flowchart illustrates the Conditional Decision Module, or CDM, which serves as the brain of AEGIS. This is where high-level risk management requirements from ISO 14971 are translated directly into executable Python code. ISO 14971 is the recognized international standard specifying the procedure by which manufacturers identify and manage the hazards associated with medical devices. Inside the CDM, atomic conditions like minimum sensitivity floors and maximum drift allowances are aggregated simultaneously using strict Boolean logic to create a single deterministic outcome. The CDM operates on two parallel tracks. Track 1 governs new model deployment. It evaluates the candidate model against a four-category taxonomy: approve, conditional approval, clinical review, and reject. Track 1 enforces a rigid priority hierarchy. Hard safety floors, such as a strict minimum sensitivity required to avoid missing a lethal sepsis case, are evaluated first. If a model fails that safety check, it is immediately rejected. Excellent performance in other metrics cannot override a fundamental safety violation. This diagram illustrates Track 2, the parallel post-market surveillance track, which generates an independent alarm signal. A dual-track system is operationally required to separate the governance of the new update from the surveillance of the model currently operating in the hospital. While Track 1 evaluates the new candidate model strictly against the static golden dataset, Track 2 simultaneously evaluates the currently released model against the live drifting dataset. These tracks operate completely independently. If the hospital's patient demographics shift suddenly, Track 2 can fire an alarm to signal field degradation, even as Track 1 simultaneously approves a retrained model that successfully adapted to those shifts. This dual-track architecture satisfies the FDA's requirement for static equivalence checks prior to a modification, while simultaneously meeting the EU's mandate for continuous real-world risk management. We can observe the system's behavior through a simulated 11-iteration deployment, where the sepsis model processed thousands of patient records through the AEGIS infrastructure. In the early stages, the system operated seamlessly. It detected minor, safe improvements and automatically approved updates entirely within the FDA PCCP bounds. But at iteration 10, the system encountered severe covariate drift in concoming patient data, and AEGIS abruptly halted the deployment pipeline. On Track 1, the new candidate model sensitivity plummeted to 0.428. This violently breached the absolute safety floor of 0.65, forcing an immediate, non-negotiable reject decision. Simultaneously, on Track 2, the live model currently deployed in the hospital was failing against that exact same demographic shift. The CDM detected this regression and fired a critical alarm to mandate immediate post-market surveillance escalation. Without AEGIS, the hospital's existing adverse event protocols would have missed this statistical decay. A failing clinical algorithm would have continued operating silently on a hospital floor, generating confident but incorrect sepsis predictions. By combining strict data separation with deterministic logic, the framework intercepted the most dangerous state in medical AI, the moment when no safe update exists and the live system is actively failing. It caught the degradation before a single patient was harmed. Tabular sepsis data provides a clear example, but the ultimate power of the AEGIS system lies in architectural abstraction. This diagram shows AEGIS applied to automated 3D MRI brain tumor segmentation using convolutional neural networks. For this context, the data modality shifted, the architecture changed, and safety thresholds were recalibrated. Yet the core infrastructure modules remained universally unchanged. The Boolean logic governing the deployments, the data compartmentalization, and the surveillance protocols operate identically, regardless of whether the system is analyzing a 1D vital sign array or a volumetric brain scan. Scalable post-market governance cannot rely on hard-coding highly specific medical rules for every new algorithm. It requires an invariant, deterministic architecture that allows any AI across any clinical domain to learn continuously and safely.